Okay, good morning, students. Today is June 21st, and we're going to review the process to calculate this redistribution of normal stresses because of the influence of the shear, okay? And this is the situation, right, where this is the reason why many, I would call it academic people, right, from this side, they don't like these formulations because we started, right, chapter 1 saying that kinematic hypothesis is acceptable. We accept it. And that means that any straight section travels vertically and rotates, right? And we went on with that formulation, and we said, okay, sigma is equal to minus m y over I. And then we went on and said, okay, now we have to accept that the shear stresses deform the section. But to calculate that, we use the expression that we obtain after assuming that the section is straight, just rotates. So in reality, it's some contradiction. But anyway, the result is that it is kind of acceptable, the results that we obtain. And that's why we explain it. But the final result is that because of the shear, there is some separation from the result, the original result, which was that the section is straight. I mean, does this and that. So now we have to accept that it does this, that, and also a little bit of distortion. So the section is not straight anymore in the presence of shear. Okay, and that's the idea that I want you to keep in your memory. Okay, so the method that we are using in order to calculate the final result, which is a redistribution of stresses, it's a combination. Okay, in detail, we can apply this assumption by Taylor, but in a more practical way, when we calculate the maximum stress, we use Shady's theory to calculate effective breadth. Yeah, those are the concepts that have to be clear in your mind. Okay, so we're going to review Taylor's process, and then first, for the simplest case, this is something that we did last week, and then we're going to go with the example that I asked you to review. Remember, I asked you to review. The section is a square section, and that's the section that you have to analyze in your homework. Okay, so we're going to spend some minutes on that, checking the details, and then at the end, I'm going to see if there is any. Well, I'm going to make an explanation of the next homework, explain the details of why I'm asking this, and more or less try to answer your concerns. Okay, that's the agenda for today. Let's see, here we have. Isaac, can you see my full screen? Isaac, can you see my full screen?
Not yet.
Not yet? Shoot. Okay, let me change this to here. Let's see here. Yeah. Can you see it now? Isaac, can you see it now?
Yes, doctor.
Okay, thank you. So this is the example that we started to consider. It's a flat bar. That's the word for platina in Spanish. And we have to be careful because this is the expression that we need to apply. Okay, so this is the first term. It's the term that comes from, this is pure bending theory, okay? With that, we deduce this one here. And this here, that's the reason why some people do not like these results, is because this result comes from a pure bending theory, meaning that there is no influence from the shear stresses. And finally, this term here was proposed by Taylor in order to recover equilibrium, okay? This is, if you integrate this stress distribution, right, in the section, you recuperate the moment. If you add something to this distribution, then the first two terms integrated will produce a different result from the bending moment. And we are in trouble because we have to recuperate the bending moment because of equilibrium. So this is what he proposed, Taylor proposed, okay? So he said, okay, we're going to subtract, okay, the result of integrating all of these stresses on the section. If we do that, we obtain this delta M. So this is the moment which avoid having equilibrium right now. So if we apply this moment and assume, one more time, and assume that the stress distribution follows this linear relationship, okay? At the end, the three terms will produce a normal stress distribution which recuperates the bending moment, okay? So integrating this and integrating that, we obtain the same value, delta M, but with different sign, okay? So integrating these two cancel each other, and then we will have from this term here, the effective moment that we need, M, okay? To calculate that, remember, please remember the concept. This is chapter 2, okay? What we do is we define a sector here from a certain position Y, okay? And in this section, let me draw here. Then let's change color. Okay, on this sector, okay, we have a force, let's call it F sub S, and then we have a differential. On the other side, okay, on this, we also have Fs, okay? And when we move from this cut to the new one, there is this force, net force here, which avoid having this segment in equilibrium, okay? And because of that is that we need to include or to consider tau in our calculations, okay? So to calculate this, in the first step, we go from a cut at any position that you want. And in that cut, we are going to calculate the shear stress, okay? And the sector has to finish, has to end in a point where we know the shear stress. And of course, we, according to our explanation, there are certain points where we know that the shear stress is null, okay? We have either that the edge is free, or in other cases, we can consider the consequence of having a symmetric section, right? In those two cases, we know that in those points, the shear stress is null, okay? So in this case, the sector, okay, starts at the point, Y and ends at the top of the flat bar. So this is our sector. This is the first moment, and we have done this many times, okay? This B, we have to be careful because this B is the width at the point where we do the cut, okay? This Y is measured from the neutral axis, okay? So let me insist this because there were some problems in the previous quiz, okay? This Y is measured from neutral axis. Okay, and after that, there is another term that we need. This is the integral term, okay? And this term is in here, in the second term of the expression that we're trying to apply, Okay, here you see that this is this. Okay, now this term here, we have to be careful because for this one here, do you remember, does anybody remember where did we get this integration? Anybody remembers where do we introduce this integration? Anybody, do you remember? Everybody review your class notes, and I want you to tell me, why do we need this integration here? Where, in what point of the process we were required to integrate this? I'll give you a couple of minutes. Please, I'm going to ask a couple of people, okay? If you don't answer, the rule is simple. Do not answer. That means that you're not here, and you don't have to be in
Doctor,
session.
from the distortion of the section, from the shear stress.
No. Specifically, why, in what point we introduce this? Let me ask somebody, please, okay? Because I need more people to participate. Okay, I'm going to ask somebody. Okay, the last part of the list here, we have Miss Acuña. Miss Acuña, do you remember how did we introduce in our analysis this term here? Do you remember, Miss Acuña? Miss Acuña, are you there? Please don't make me waste time. Oh, she's not here, okay? She's not here. Miss Puertas, can you remember how did we get this term here? Miss Puertas, please wake up. Oh man, there is somebody else who is not here. Isaac, please. Mr. Carriel.
Good morning, doctor.
Do you remember where did we get this term, this integration? Oh? Can you look it up? You can look it up in the class notes. No? Miss Poveda, are you there, Miss Poveda? Can you explain us how did we get this term here?
No, doctor, I'm looking for, but I'm fine.
Okay, you're here. Okay. Please, this term here appears when we calculated the U. Okay, that's the axial displacement. Okay, so in that point, we introduce this term. Okay, so this is employed to calculate U. Okay, so we obtain the U dy, okay, and then we integrate it, okay. With du dy, we obtain with shear stress divided by G, okay, and with this du dy, we integrate it in order to obtain U, and that's how this integration appears, this integration. Now, that's something that we have to remember, because to calculate this term here, we go from the neutral axis, which is the point that we consider as our reference, okay? And we integrate from here until the cut, the point where we want to evaluate U. So we have to be careful, right? To calculate Q, we need this sector. To calculate U of Y, okay, we need to integrate from here until here. Okay? Clearly here, I'm showing you the ends of this integral from 0 to Y. This thing here, it's integrated from Y to H over 2. Clear, showing the ends of the limits of the integral. And the rest is easy, right? We put this term here into here, and it's just a matter of integration. The variable is, in this case, is Y. Y. The rest is just simple, just evaluate it, and that's it. You evaluate this at 0, and yes, since we are considering the difference, uy minus u0, of course, we have to obtain zero, because you are saying, when you evaluate this at y equals 0, basically you are saying u0 minus u0, that's 0, definitely, okay? Okay, so there. If you evaluate this at values of y less than 0, then you simply obtain the displacement, axial displacement, okay, as we have seen here, below the neutral surface. Okay, so you can obtain positive or negative values. Okay. And after that, okay, we simply replace. We have minus E over GI. This is P, this is force per unit length, and this is the term that we just obtained here. Okay, in this process, we have to be very careful, right, with the units. Okay, so since we have so many terms, okay, what we have to do is we have to be, after certain number of steps, you have to check. Let me write it down. So this is a warning for you. Okay, this is just a suggestion. Okay, check units or terms there a number of steps. Okay, because there are so many terms that we can easily get confused. Questions so far, people? Questions? No questions. Okay. So we have the second term here. And then for the third term, we have to integrate the stress to calculate the net moment on the whole section. And that's delta M, that's the value that it avoids equilibrium. Okay, this delta M is exactly the value that it's taking us away from equilibrium. So what we do is we integrate, and this integration is over the whole section. Okay, so this is over section. Okay, the other two, you obtain distributions. In this case, you obtain a single value because you integrate over the whole section. So in this case, you go from minus h over 2 until h over 2. And this dy, okay, this dy, okay, since there is no variation in the z direction, this is the z direction, okay? So what we're going to assume is that the distribution of stress in the z direction, it's neglectable. Okay, that's why in here you see that there is no dependence on z. Okay, so this here is dA is equal to dz dy. And the integration of z will give us b, right, which is this dimension here. Why? Because we assume that the thickness is small and the variation of the stress in the thickness is neglectable. So if we take a very, I mean, something which is not very thin, right? Then in this case, this assumption is not applicable. And we will have to think about how to assume the variation of the stress in the thickness. Not in our case, not in this course. Okay. Now, after we complete to calculate delta M. Okay. See, you see here that instead of dz, we have obtained the integration of this is b. Okay, we can proceed with the calculation. Okay, and we are integrated in y, and that's easy. So here, as we did in last session, the units are correct. See, force times length. That's something I said a couple of minutes ago, right? Every certain number of steps, stop there, check the units, because it's so easy to make it, to forget a term or something like that, okay? But this is just algebra. And the integration is just simple integration of polynomials that you should do it. And finally, we have the whole expression that we can employ, okay? Here, we have all the expression again, and I have replaced, you can see that I have 1 plus nu, that this comes from E over G. Okay, in that case, we cancel G because G is equal to E over 2, 1 plus nu. So that's why we have this. And this is the integral of Q dy over B. Okay, now we have this delta M, we know this value. And this is what we are going to do. So we are going to estimate the distribution because of this load in a simply supported case. Okay, now this is something which is it's not really it's not correct. I guess the word would be it's not adequate, and I'll explain to you in a few minutes when we explain the homework. Okay, the first problem of the homework. But anyway, this is just an example. Okay, with all of this information, we can proceed and we can calculate delta M. Okay, so we have this integration over the whole section, and this is delta M. Okay, so if we apply the first two terms, this value of delta M will take us away from equilibrium. So we have to apply it, but with different sign. And that's what we're doing here, okay? So this is a summary of that. And have to be careful because in this case, in minus y, at y started at minus 10, starts at the bottom. And then we go up, but in our case, we in the first column, we come down. Okay, so we have to be careful with that. Then we have this function, the integration. Then we go flexure, pure bending, that's minus my over I. So that's a straight line. The second one is the correction. Okay, in that case, we use the integral that we have in the second column. In the third one, we apply the formulation of Taylor. That is, we assume that in order to make this correction, okay, to recuperate the equilibrium, we assume that this delta M produces a linear normal stress distribution. This is an assumption. And basically, it's just a practical assumption. There is no physical justification for that, okay? It's just that. And the results are decent, okay? So, and finally, we get we combine, okay? And we see that originally, we had a stress of 187. And if we include the influence of this shear, we turn into 190.1. So this is a small increment, right? So, and we are going to consider that that's the case when we have these simple vertical elements. When we have a vertical element combined with a horizontal element, like a flange, in that case, because of this change in direction, there's going to be some distortion of the section around this corner. And that increases the normal stress in this connection. Okay, so that's this increment is our objective. This is what we want to calculate. Okay, so if we consider the three terms, okay, we are away from the normal stress distribution from pure bending. Okay, we do this integration, numerical integration, and still recuperate the bending moment in the section. So that means that we are in equilibrium again. Okay? So you integrate pure bending, shear normal stress, and you get M. You integrate the shear stress correction, and you get delta M. If you integrate the correction by Taylor, you get minus delta M. So you add the three terms, the two cancel, and you get M. And you go back to equilibrium. Okay? So here, I would like you to help me. I would like to establish like a procedure. A procedure in order to develop this process to calculate the normal stress distribution. Okay. Let me go to the last page. Ms. Valdez, if you have to calculate the normal stress distribution, considering the influence of shear stress, what's your first step in general? Ms. Valdez.
Yes, doctor. Calculate the first part, the correction.
No, to calculate that, what you need? Mr. Chiriboga, what would be your first step? See, this is not my procedure, okay? This is your procedure. So let me change color. Mr. Chiriboga, can you help me, please? What will be the first step? Please don't draw on my screen.
The inertia.
The what?
Well, the inertia.
The inertia. Okay. I'm going to just write down. I'm not going to. Okay, inertia. Okay. And how do you calculate inertia, Mr. Chiriboga? Mr. Chiriboga, how do you calculate inertia? Mr. Chiriboga, are you here?
Yes.
Oh. Okay. How do you calculate I sub C? Give me the formula to calculate I sub C. It's equal to what? Mr. Kimi, Andres Kimi, do you remember how to calculate the inertia, the formula to calculate this inertia?
Good morning, doctor. Inertia is B 1 divided by 12.
No, that's specifically for a square section. But give me the formula to calculate that. Now, Mr. Cedeño, Jarry Cedeño, do you remember the formula to calculate I sub C? It's an integral. Mr. Cedeño, Jarry Cedeño. Come on, people, don't make me waste time.
We elevate to
No. See, I'm trying to ask many people to participate. That's why I'm calling somebody in specific. Mr. Cedeño, are you here? No. Okay, Isaac, please. Ms. Dominguez, what's the formula to calculate the inertia? Ms. Dominguez.
Yes, doctor. Integral Y times the derivation of area.
Yes. Okay, and this is for a rectangular section. That's the result that gave Mr. Kimi. Okay, what's next step? Let's call somebody. Mr. Paredes, Luis Paredes, what next step after calculating the inertia? Mr. Paredes, what's the next step after calculating the inertia? We want all of this expression to be calculated. Mr. Paredes.
Calculate BQ.
No. Please, I'm asking somebody specifically because I want everybody to participate. Be patient, okay? Your time will come. Mr. Paredes, are you there? Isaac, please.
You tell Daniel or Luis?
Mr. Luis Paredes. I'm here. I have an order here, so I'm just following that. Mr. Cedeño, Axel Cedeño. Please, Isaac, take him out. Don't doubt. Because I don't want to waste time. Mr. Cedeño, what's the next step?
We have to calculate the normal share distribution.
Come on, yeah, but to calculate this, okay, this is something that we have to apply.
Okay.
Mr. Ortega, Andres Ortega, are you there? What's the next step?
Calculate the bending moment.
Yeah, but that's something that we have before. Come on, let's go to this term here. Mr. Ramirez, Jose Ramirez.
GI.
See, you are completely lost, Mr. Ramirez. I is this. We already calculated this. What is this G, Mr. Ramirez? What is G, Mr. Ramirez? It's G. Please start reviewing, start studying. It's not my fault. You are not spending enough time with this material. Unfortunately, it's being recorded, okay? Mr. Chin Chin, what's the next step to calculate this? Mr. Chin Chin.
Calculate the first moment of area.
Yes, Q of Y. I'm sorry, Mr. Chin Chin. Let me ask you something. This is kind of personal. Your last name is Chin Chin or Chin Chin?
Chin Chin. Join.
Yeah, but you should use a tilde in the second I, isn't it? Right?
Can you repeat, please?
You need to include a tilde in the second I because it's Chin Chin, right?
Yes, but no, these with tilde.
Okay. So we are fine. We are fine. Okay. So we calculate this. Mr. Soria, what's the next step after calculating this? Remember, this is for a sector. Okay. And this goes from Y until top. Let's call it top. Okay. What's next? Mr. Soria, what's next?
The integration.
The what?
The integration of Q times dy by.
Yes, and this is what we call the integral, okay? And we have to be careful because in this case, Mr. Soria, okay, what are the limits of this integration, Mr. Soria? What are the limits of this integral?
0 to x to y.
S. Yes, that's very important, okay? And after we do this, we can evaluate this term here, the second term. Okay, good. Miss Arechua, what's next step now?
Calculate the px.
What?
Calculate the px for later the bending moment.
No, that's already been calculated because we do this as part of the equilibrium relation. And P of X is data. This is data. This is the load per unit length which is being applied.
So, like, I suppose that we have E and J. We calculate all of this term.
I'm not following you. Mr. Fuertes, what next step after this? Mr. Fuertes, what next step?
Good morning, doctor.
What next step? No?
No.
Mr. Aizaga, what next step?
Good morning, doctor. Integrate that value.
Yes, to calculate delta M. And the region of integration is what? From where to where, Mr. Aizaga?
To the neutral axis.
No, Mr. Dominguez, Salim Dominguez. Integrate in what region, Mr. Dominguez?
The whole section.
Yes, over the whole section, yes. Because you need to calculate how much moment is out of, it's in imbalance, right? And then we can apply the whole expression. Okay. Now let's go on with people. You see that there are some of you who are completely lost. Okay. Unfortunately, this is being recorded. Okay, so you have to start reviewing. You have to spend time. Okay. I'm not going to say much about that. Okay. Let's go on. Now, this is a section that we're going to analyze now. Okay. It's a barge. It's, of course, it's simplified. Okay, let's assume that we have this square, it's rectangular section. It's similar to the section of a barge. I know the barge is more complex than this, but in a simplified way, this is what we can see. Okay, so we have B, that's the beam, and H in this case would be our depth. Okay. And we're going to assume that the thickness in general is uniform over the whole section, right? So we want to calculate the normal stress distribution in the section, considering the influence of the shear stress. Okay, so let me go back. Okay, the inertia is something that we have to calculate. Okay, Mr. Vasquez, okay, in class, we implemented the procedure in order to calculate the inertia, okay? And for that, one of the intermediate steps is the calculation or the determination of the position of the neutral axis. In this case, Mr. Vasquez, where is the neutral axis, Mr. Vasquez?
The neutral axis is going to be in the half.
Exactly. If you don't get the average, let me write on the left. If you don't get the average equal to H over 2, okay, what you should do, Mr. Vasquez, if you don't get exactly that, what do you have to do?
I think that I applied the formula that is the summation of.
No. What I'm asking you is, that's something that we expect, right? Please take a quick look, every one of you, after class. Review the quiz that you gave me, and check if you got the average is different than H over 2 in the third exam, in the third problem. Mr. Guaman, why you laugh? If you don't get H over 2, that means that there is something wrong with your calculations. And you shouldn't go on, return, and check. That means that you're thinking. Okay? So, if you have this situation, you know where the neutral axis is, right? You can save some time, right? Because you know that you have to calculate with respect to this axis. So the integral will be the area of the deck multiplied by this distance squared plus the inertia of the deck. That's BTQ divided by 12. Twice, because you have here, you have the same as in the bottom. And you have to add the inertia of the sides. The thickness, H cubed, which is a very large quantity, divided by 12, and then multiply by twice because you have two sides. You don't need to establish this table because you see that in that case, immediately you recognize where the neutral axis is. Okay, so that makes it's something that we should you should have in your memory. Okay, now let's go on. So after that, somebody said that we're going to consider the calculation of Q. That's the first moment. And this is it. Okay, so we have to go and define, this is the sector that we're going to consider. And we're going to go from here until here, both sides, okay? Now, let me draw in 3D. So we have something like this. And like this, okay? So in this direction, I have Fs plus the differential. In this direction, we have F sub S, okay? Now let's go on. Let me erase this. Okay, now let's go on. Now, this cancels that, right? Now, we have said that we have only one expression and we have to have only one single unknown. Otherwise, we couldn't solve this problem, right? And what's this unknown? Well, the unknown is one value of tau. So in this cut, the tau would be that one. So that's our tau Zx. And this is equal to this one here because of symmetry. So this is equal to that. Now, you are seeing that the sector starts here and ends here. So this is the area of the sector, but we have to be careful because in this case, the tau, it's twice, okay? That's what I'm writing here. Okay, so in this case, we consider both sides. So from here until here, that's the width. And that's B, that's the beam, minus 2S. Because we take this part and this part here. Okay? Multiply by the thickness and multiply by the position of the centroid. Okay, so the centroid is located from the neutral axis at the distance h over 2. We have to be careful because in this case, clearly, to avoid confusions, we recognize that B is equal to twice the thickness. Okay? Any questions about these, people? Any questions? No. Okay.
Doctor,
So,
excuse me.
yeah,
The B equal to thickness is because there are two sides.
Exactly. Exactly. Remember, what we do here is this. Okay. We know that the stress or Fs, okay, this is the net force on the section. Okay, and this net force on the section is the integration of a sigma in the sector, right? So we have the integration of bending moment I over inertia. There. Okay. And then is this? Yes. So, and this is going to be equal to what? To have equilibrium. We said this is equal to dx. I'm sorry, this is this. I'm sorry, this differential. Please don't write on my screen. Okay, so this is this differential. Okay, so this area here is equal to dx times t, okay, plus dx times t on the other side, and both are multiplied by tau cx. So this is going to be equal to twice there. Okay. People?
Yes, doctor, thank you.
Okay, that's your B. Okay, so that's the first step. And we have not completed the first step because we have a different geometry than the one that we had before. So this is just for the deck, okay? So we have a rectangle, and the rectangle has a constant distance of the neutral axis, of this centroid to the neutral axis. Now, let's go now to the side, okay? Again, we make a cut and we integrate from there all the way up to the other side. Again, here, we have something like this. Sorry, it's just up to here. Okay. So down here, we have an area, similarly down here. Again, we have an Fs plus dF. Here I have an Fs, this cancels that one, and we need equilibrium. And this is the stress that we need to calculate. But we have this plus that. And we assume, because of the symmetry, they are equal. And again, you can read here that B is equal to twice T. Okay, because we are considered all the way up to here. Somebody could say, okay, we could consider only, that's some authors to integrate from here only up to here. And the stress here, how much is the stress here? Mr. Zurita, how much is the shear stress in this cut? Mr. Zurita, are you there? Mr. Zurita.
Yes, doctor, good morning.
Good morning. How much is the stress here? Shear stress in this cut. Mr. Guaman, you were saying something. Mr. Guaman, how much is the shear stress in this cut?
Sure.
Mr. Guaman? In this cut.
In the middle of the section is 0.
I cannot hear you, Mr. Guaman. We have problems. No, okay. Don't worry. We understand we have some problems. I'm seeing you. You are trying to. Let's see somebody. Mr. Paredes, Daniel Paredes. What is shear stress in this cut here?
Good morning,
Mr.
doctor.
Daniel Paredes.
Is 0.
Yes, and because why is that?
Because it's the formulation is BQ over.
Please be physical right now. Why we need the shear stress to be 0 in this cut? Physically.
The shear stress is perpendicular.
Please, Mr. Pesante, be patient, okay? Because I'm asking somebody. Be patient, okay? Your time will come. Miss Santos, why the shear stress is 0 in this cut?
Because it's at the symmetry.
Yeah, no, somebody said that already, but physically, tell me why.
And the
Yeah,
at
exactly.
that point, the
The
shear
shear
stress
force,
is
no, the shear forces in this direction has to be
equal. So
yeah. At this point, they have to change sign. So you go right, and then here you have to start going to the left. Why? Because you have to
sign.
cancel.
Yes.
Because you have only applied vertical forces. Okay?
Yes.
If you don't make me mad, I'm not going to give you, but I could give you force like this and force like that. And in that case, you shouldn't have 0 shear force, shear stress in the symmetry axis. Don't worry, I'm not going to do it, but you can see that there are more complex situations. Okay, fine. There are some people who want to integrate from here until here. In that case, B will be equal to T. But in that case, this area will be different because this area will be only from here until here. That's all. So you take the 2 on both sides, and at the end you get the same. But you have to be very clear if you are taking both sides or only one side. Okay, that's what I'm giving you. Now, this is simple. This is for the whole deck. This is just for this part here, plus this one here. You remember that there was a T/2 when you have one side, and the 2 in the denominator cancels when you multiply by 2. Okay? Questions so far, people? Okay, let's take a break here. Okay, 5-minute break. So have at hand the class notes where we have this example. Okay, so you can follow these formulations, which are kind of long. Okay. Okay, 5-minute break.